Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 16 and we will be today dealing with various coolants which are responsible for maintaining a cryogenic temperature and fluids required in actual experimentation. We will start from where we left again in the previous lecture, and this was the measurement setup which is there. Please understand, the cryogenic fluids will be flowing within this chamber here. So there is a small chamber here, right, at the bottom here, which stores basically the qubit package. The qubit package, which should be kept approximately at around 10 millikelvin, is placed somewhere in this package, right? And this is actually sort of vacuum packed inside enclosure, across which you will have interconnects running for controlling the qubits as well as reading out from the qubits. Now you might even ask one basic question, that why do you require such a huge sort of setup in order to maintain something like this, right? There is a problem here. I will tell you what the problem is so that it's clear to you why we are studying this course at the very first instance. See, your qubits are generally maintained at millikelvin or somewhere around very low temperature, right? So your qubits are stationed at few millikelvins, right? Maybe tens of millikelvins. And your electronics, as you know, is stationed somewhere around 4 Kelvin. Let's do one thing, that let's not take care of the electronics and let's push it to 300 Kelvin, right? We placed in a region which is 300 Kelvin. Now when it says 300 Kelvin, please understand the temperature has risen from 4 to 300 Kelvin, large increase in temperature, which will therefore result in large amount of noise, and these are known as thermal noise. Not only that, if you place your electronics very far away from the qubit, not only maintaining low temperature for the electronics is difficult, but you also add the resistances and capacitances of the extra wires which actually require to go from the electronics towards the qubit. That also adds to the noise, and therefore since your signal is anyway weak because it's a very low temperature, your signal to noise ratios are actually very small. Once they are very small and the noise is much larger as compared to the signal flow, it will become very difficult for one to actually manipulate the signal or read the signal or try to manipulate the qubits even. So both ways it will be a trouble, and that's the whole logic to keep the electronics very close to the qubits. But the cost you pay for it is that two things. One is that we are still not very clear about how does the device behaves at ultra low temperatures. So we cannot a priori predict the behavior and the characteristics of the fed device, for example, at such low temperatures. Not only that, there is another problem, and that problem is that the volume where the qubits are placed or even where the electronics are placed are very restricted, right? So the space is a big issue here. And the last point is, these electronics, since they are operating at relatively high frequency, they will also generate heat, right? So there might be a thermal gradient already available because of the electronics. So these are the grand challenges which as experimentalist one has to be very careful about and ensure that there is no large amount of thermal gradient which is happening in a system. And that's the more so the reason why as a designer or as an experimentalist you require to have the qubits and the electronics very close to each other. So the qubits are pushed to around 10 or 20 millikelvin and the electronics is pushed at somewhere around 4 Kelvin to 5 Kelvin and so on and so forth, right? Anything larger than that then entails more amount of noise, and then you start losing the gains which you get out of qubit. So that's the reason, and that's the reason if you look very carefully at setup A here, it looks so complicated and it's so large number of wires, interconnects, proper hermetic seals are there so that there is no loss of temperature at any one of point. Proper vacuum is generated at each and every place so that there is less amount of dissipation through convection currents and so on and so forth. That's the whole idea behind it. Please understand, you need to therefore do all these operations at very low voltages, right? So, and as I discussed with you in the previous turn, low voltage is primarily meaning that sensitivity is larger, and that makes your life difficult as far as quantum computing at low temperature is concerned. So, that was the motivation. Let me now come to the outline of the cryogenic coolant, or how many types of their properties of cryogenic fluids, and then we will give you an example setup of the helium cryostat. Now, what are cryogenic coolants of fluids? Basically, coolants are liquids or gases that absorb heat from the source and then dissipate it elsewhere, maintaining the desired temperature. It is almost like a coolant which you use in your automobiles. Most of the automobiles do have a coolant which tries to cool down the engine to a larger extent. The same thing happens here, that it pushes down the temperature right up to 4 Kelvin by an external source, and these are all closed loop. So you don't have to every time you do an experiment pour liquid helium and liquid nitrogen, but these are closed loops, so they will maintain proper temperature gradient within the region where you are actually using your electronics. Now, why do you require cryogenics? We have already done that you need to preserve low temperature at very and accurately. You need to preserve, used for quantum computing. Also, they are very much used in superconductivities and for space exploration. So and of course preventing overheat of sensitive devices. So as we had discussed with you, as the temperature varies too much, the threshold voltage changes, you can't predict therefore a priori the current, and therefore you need to maintain the temperature beyond a point. You don't expect to have overheating of systems and devices. Now, another purpose, which is the last one, is the space exploration part. Here, if you look very carefully, any spacecraft which travels to outer space faces drastically low temperature, right? So, there is also a demand from our space organizations across the world to have not only radiation hardened devices, but also low temperature variant devices, right? Or extremely low temperature variant devices to be generated, for especially for space exploration purposes. So, these are the few sort of purposes of cryogenics. Let us look at the basic cryogen chart, which generally is preferred when we do it. So, on the left hand side is basically the temperature variation, 300 Kelvin right up to 0.01 Kelvin. 0.01 Kelvin basically means 10 millikelvin. 10 millikelvin. So, we start from 300 Kelvin and go up to 10 millikelvin, and these are actual benchmarks or points which you need to take care of. One is 77 K approximately, and that is what is known as the liquid nitrogen. Look at this point. So, this is around 77 K we are talking about. Then we have a liquid helium, right. So, we have, this is liquid helium is around 4 to 10 K. So, one is liquid nitrogen, another is liquid helium. And if you go to deep space, typically you reach to a region which is about 2 to 3 K is the deep space sort of temperature. And if you further go down where the qubits are kept, at about 10 millikelvin is where the qubits are placed. So, let me write down here 10 millikelvin, you will have qubits. So, these are the 4 major pointers which the designer generally sees, that we first generate models for 77 K, go right up to 4 K, and then go to about 2 K, 3 K or 1 K. And so, you see there is almost a sort of 2 order decrease here, which you see from 1 to 100, 1 by 100 means 10 to the power minus 2 sort of change, which you see here. Let us look at the second graph here, and the second graph gives you the computational gain, speed improvement which you get versus the energy requirement. So, if I assume that normalized, that your energy requirements are 1 at 300 Kelvin, it becomes approximately 10 to the power minus 2 at liquid helium, which is around 3 Kelvin, and reaches up to 10 to the power minus 6 when you go for this much amount of joules here. So, if you are normalizing with respect to 300 Kelvin, and if you are working with qubits, quantum qubits, then the energy which you have is 10 to the power minus 6 joules, which means that I can operate with about 10 to the power 6 times lesser amount of energy at when we are operating at around very low temperatures, right, at cryogenic temperatures. Similarly, let us look at the computational gain which we get. If I again normalized with respect to 300 Kelvin, then the speed gain is 1. I am normalizing with respect to 300 Kelvin, obviously the value will be 1 here, but subsequent value is speed gain is 10 to the power 3, right. So, liquid helium you get a gain of 10 to the power 3, right. So, liquid helium speed gain is 10 to the power 3. Further down if you go, I get 10 to the power 9, which you get increase in the speed. So, you see a 3 order increase in the computational speed happens when you go for low temperature, and you get a 9 order increase in the value of the speed gains when you go down to millikelvin region of operation. Let us come to the last diagram on the right hand side, and the blue one is basically the cryogenic memory, the cryogenic computational part here, right. Now, the lowest in the base is basically quantum circuits operating at millikelvin. Then you have quantum computer, which is operating at 4 to 10 Kelvin around. Typically, your cryogenic memory is slightly on the higher side from 10 to 30 Kelvin, and the classical computing is happening at 300 Kelvin. So, now you must be aware of, therefore, what are the various phases at which various operations are conducted, and what are the gains of various operation and the cryogenic requirements. So, let us look at the type of cryogenic coolants which is available, and these are all commercially available. For example, liquid helium is very difficult to get otherwise, but liquid nitrogen is relatively easy to guess across the various scientific units. So, the first thing is liquid helium, whose boiling point is approximately 4.2 Kelvin, which is minus 268.93 degrees centigrade, and they are used for quantum computers, they are used for cooling superconductors, and then also for MRI machines. MRI machines are huge machines which require constant cooling because they use magnetic resonance, which is very power dissipative element, and therefore it gets heated up very fast, and therefore to cool it down you require to give large amount of coolant species, which is specifically helium. Then we have another specific cryogenic coolant, which is basically liquid nitrogen, right. So, your N2, we discussed about liquid helium here, there will be liquid nitrogen working at approximately 77 K. So, most of the research or most of the operations are done at 77 K for understanding how the device behaves at the low temperature, right, and then we proceed for 4.2 K. You got the idea. So, we go step by step. 300 Kelvin is known to us, we drop down to 77 K, that is a liquid nitrogen temperature. There we study very hard to extract the information about the device, and then we go to liquid helium, which is kept at 4.2 Kelvin. Another node, another sort of a node we say is around 27 Kelvin, which is for liquid neon. This is for liquid neon, where we use 27 K value, and these neon are used as coolants in many applications, for cooling applications. And liquid nitrogen is used for food preservation, cryotherapy, and so on and so forth. However, 4.2 is used for quantum computing, superconductors, and MRI machines. So, let us quickly go through the cryogenic properties or the properties of cryogenic coolants. And typically, the thermal conductivity is relatively much better, high, and therefore, they have much better efficiency of heat transfer from point A to point B. They can carry the heat and move from point A to point B. There is known as specific heat capacity, is basically indicates the amount of heat a coolant can absorb per unit area. So, if I have a per unit area mass available to me and you want to remove heat out of it, then I put a coolant, then per unit mass how much amount of heat it is extracting is defined as my specific heat capacity, right. Of course, density and viscosity plays a major role. It affects the flow dynamics and therefore the heat transfer efficiency. Okay. Very important, because if the transfer is not proper from point A to point B, you will never have a good amount of heat transfer from point A to point B. Now, latent heat of vaporization, typically critical for phase change cooling systems. We will not discuss about phase change cooling system at this place. And boiling and freezing point, we have already defined that for each and every sort of coolant which we have used for this purposes. This is an example of a cryostat experimental setup. Again, I am saying this to be as a closed loop one. So, this is your OptiStat cryostatic here, right, and this is part which you are talking about, right, sort of the element which actually needs to be went down to cryo. So, what you do is that you, using the OptiStat cryostat here, which is CF, you tend to move it through cryogenic storage lever, where the cryogenic is kept at very high pressure and therefore they are liquid. Once they are released, they become gases. Also, they are sometimes liquid also kept at very low temperature and pressure. Then there is a flow meter which takes care of how much amount of the cryogens are flowing. This flow meter takes care of that. And then there's a liquid helium recovery, right? Now, what is the meaning of this is basically that the liquid helium tends to leak at certain particular point or move away, or the temperature rises beyond a particular point. This helps it to recover all those values in a sense, right? And that helps you to work in that environment at a very much better manner. So optistatic, which is this one, the first one, optistatic, this one, right, is used to maintain ultra low temperatures for experimental setting. That's what I already told you. And it connects to liquid cryogen or liquid cryogen supply for cooling. So this is directly connected to the liquid nitrogen, which is this one, right. Then mercury ITC, what we refer to, is the temperature controller system, and that regulates and monitors the cryostat's operational temperature. This one maintains the operational temperature, this one. Then of course there is a storage element of cryostat, and it is used liquid cryogen, and also prevents heat transfer and minimizing the boil off point for liquid hydrogen. The siphon and the VCU voltmeter is this one. This is VCU flow meter. So let's go one by one and I'll explain to you. So basically its job is to connect liquid cryogen supply for cooling directly. And this also maintains, so this mercury ITC is a patented sort of technology and regulates and monitor cryostat operational temperature, right. Then of course there is a storage devar, which is insulated container and used to maintain the liquid nitrogen or liquid cryogens here, store the liquid cryogen here. It also tells you, or it is also preventing heat transfer and therefore minimizing boil off, which means that if you would actually keep this in open, there will be boiling off. The liquid will boil off in a gas state directly from liquid, and you will be losing these very costly cryogens to the atmosphere. And this storage device, which is very, very high pressure storage device, stores these material in the liquid state and tries to work it out, right. If you look at the VCU flow meter in the siphon unit, basically this one, this siphon unit actually does a transfer, right. Look at this and this one, VCU flow meter if you look. So LLT siphon helps you to transfer liquid cryogen from storage devar to the cryostat, and therefore there is a flow meter that actually sees the flow rate of the helium gas. Both of these are external temperature controllers in a sense. So I can do a real time change in the flow so that I know that I require maybe a larger gas or a smaller amount of gas per unit volume. There are also certain cryostats available, or even siphon and flow meters available, which are purely runs on the feedback loop, and it automatically sets, if you set the temperature of the chamber, it automatically changes the flow meter parameters so that the temperature is maintained properly at the quantum qubits are kept. Now gas flow pump and helium recovery are the two units. Basically so what has happened is a closed loop system. So once the helium comes, cools down, it evaporates, goes to the recovery chamber. At the recovery chamber, it is done a feedback loop with high pressure to convert that into a liquid, and again forced back to go into the system, right. So this is basically a closed loop system which does not require an intervention from an external source. It's basically a closed loop system, and that's the advantage of such a cryostat experimental setup. Let's finish this talk with a numerical sort of an approach which we need to look into. That let us assume that a cryogenic systems operate at 4 Kelvin and it requires 10 milliwatt of cooling power. Efficiency is given as 1%, if the efficiency of the cryocooler is approximately 1%. So typically if you take a ideal Carnot refrigerator and assume it's perfectly ideal, efficiency is 100%, which means that the cooling is absolutely best which you get, then we define that to be an ideal Carnot refrigerator. However, most of the refrigerators, be it coolant refrigerator or anyone, does not follow an ideal Carnot. And if I assume that the cryocooler is 1% efficient, then we are told to determine the electrical power required at 300 Kelvin to achieve this cooling, right. I am at 300 Kelvin, want to go at approximately 4 Kelvin, and this 4 Kelvin requires a 10 milliwatt of cooling power. Now we define a term here which is known as coefficient of performance, right, and it is given as this is given as Tc upon Th minus Tc, right? And I will explain to you what is Tc. Tc is basically the temperature where you are going to reach, and Th is the ambient which you are going to do. Now, if you want that COP Carnot is 1, then basically my Th should be equals to 0, and I will get Tc by Tc which is equals to 1. Now, if you look at the COP, this should be 4. So, I want to reach at 4, right? My current is at 300 Kelvin. So, what I do is this is 4. So, I get 4 divided by 300 minus 4, which is 4 by 296, and your COP coefficient of performance is approximately 0.0135. However, please understand that my cryocooler has an efficiency of only 1%. So, therefore, your COP Carnot ideal case, which is 0.0135, your COP final or actual one will be just 1% of the above value, which is 0.0135, and if that can be only done if you multiply it by 0.01. So, when you multiply, I get a new term here, and that term is this one. This is the new term which you get COP, right. So, this is 1.35 into 10 to the power 4. This is the COP of the actual one. Now, the required electrical power is given by P electrical is given by P cooling upon COP actual, right. So, you see, if your COP actual would have been larger, I would have actually required a less amount of electrical power. I will give an example. Let us say what has happened is this is 100 times smaller as compared to this, which means my P electrical, if I would have used the ideal Carnot refrigerator, my P electrical would have been 100 times lower. Getting my point? Which means that the amount of electricity required will be, or amount of power required will be 100 times lower as compared to the ideal case. Okay. Now, therefore, given that P cooling is 10 milliwatt, why P cooling is 10 milliwatt? This is already given to you here. You see that for 4 Kelvin it requires 10 milliwatt of cooling power. So, I already know that my P cooling, I already know COP actual. I divide 10 to the power minus 2 by this much, I get 74.1 watt as the value of P electrical, correct? Which means that the amount of power I required for 300 to 4 Kelvin shift is approximately 75 watt in this case, right. Quite a heavy power which you are actually drawing from the rail. Please understand, this power will be dissipated somewhere within the system, and that is the bottleneck or the challenge as far as cryocoolers or cryogenic systems are concerned. So, with this, let me recapitulate of what we have done till now in this lecture. At least I gave you an idea about the motivation for doing cryo, right. So, we first discussed about the motivation for doing the cryo, and I told you about the noise factor and all those things, motivation for cryo. Then we went for cryogens or the cryofluids, right, which is important for maintaining temperature at 77 K, 300 K we do not require, 77 K, around 3 to 10 K. This is liquid nitrogen, liquid helium, and then if you go further down, you will also have 10 millikelvin where you require. I also showed you the various types of cryogen, and I showed you actual cryostat measurement setup and what are the various functionalities of the equipment which are there in the measurement setup. Finally, I ended up using a mathematics and a numerical example to showcase that if you want to move from 300 to 4 Kelvin, you need to substantially give large amount of power just for the temperature to move from 300 to 4 Kelvin. And this or motivates the idea that as you make the temperature go further down, you require more and more power to actually require to do it, right. And that is what I wanted to showcase to you in this lecture. When we meet next time, we will start doing the subsequent part of the lecture series. Thank you very much.